Hello, welcome back to the channel. So in this video, we'll be looking at, we'll be continuing with molecular point groups. In my previous video, I have covered 3 point groups which belong to MLS, molecules with low symmetry category. So here I'll be taking 3 more point groups from MHS, molecules with high symmetry, CN, CNV and CNH. So all these examples, whatever I'm taking for these point groups, they have, for all these examples, I'm giving 3D animation support. So to completely understand the things, you should watch the video till end, and at the end even definitely I have given summary of all this, and so that from that summary we'll be easily able to identify if a molecule it is belonging to these 3 point groups. So to understand all these things, watch till the end of the video, and let's begin with the video now. Okay, let's begin with the video. So in my previous video, I have given a brief account of point groups, and even I had started with the first type of or first category of point groups known as molecules with low symmetry, where under this heading 3 different point groups can be covered. C1, which refers to a point group where only symmetry element or only symmetry operation possible, it will be identity. Whereas in case of Ci point group, along with identity, even inversion center and inversion operation will be possible. And the other one, it is Cs, where along with identity, we will have one plane. So all these are considered to be molecules with very low symmetry. The other name for this, all these together or individually, even it can be called as non-axial point groups, because we don't have symmetry axis in this case. So we are missing that symmetry axis of symmetry. Therefore, we can even refer this as non-axial point groups. Okay, now let's go to molecules with high symmetry. So in fact, under this heading, molecules with high symmetry, 7 different types of point groups are possible. And in this video, we'll be taking only 3 out of that, right? So in the last part of the video, in the last part of my previous video, where point groups and MLS, molecules with low symmetry, they were described, there are even all different types of point groups that are possible under this heading, molecules with high symmetry. That was given. So totally 7 different were possible. In that, 3 will be considered today, right? Okay, now let's begin with the first one. First one out of those 7, it is Cn. See, Cn here, n it refers to again axis, and usually in all these cases, Cn, Dn, whatever it is, n it represents the order of axis. So if n is written, it simply shows that in this case we have axis of symmetry, and on that axis symmetry operation, rotation operation, that will be possible. So these point groups, they are even known as cyclic point groups, and in this case H that will be is equal to n. So H, we know it's order of point group, and it is nothing but total number of symmetry operations, not symmetry elements, total number of symmetry operations possible in that, on that molecule. That is called as the order of the point group. That will be n here. So whatever is the value of n we write here, that many number of operations will be possible in the molecule belonging to this cyclic or CN point group. Okay, which are those operations? Easily we can predict. If we have just axis and nothing else, then on that axis totally n operations will be possible. But what we can consider is that on a axis with n order, of course we consider only n minus 1 rotations on that, and last rotation it will be considered to be identity. So therefore now on Cn axis we can say that identity operation, of course it is possible, and except identity we can have n minus 1 rotations. So we shall understand this with examples. When I take examples, definitely we understand this. The first example that I am taking is C2, point group C2. Cn, it is in general. Now this molecule which I have considered here, hydrogen peroxide, in its open book conformation. Of course, there is other conformation, planar conformation possible for hydrogen peroxide, but in solid state hydrogen peroxide, it goes to this open book type of conformation where it is a non-planar molecule. Fine. So here the only operation possible on this molecule, it will be C2 rotation. So we have an axis of symmetry, and except that axis we don't have anything else possible. No other symmetry element, no other symmetry operation except this axis of rotation, it will be possible on this molecule. Of course, identity, it will be there everywhere, so it need not be mentioned. So now you can look at how C2 axis will be there here. So this shows that this hydrogen, it is projecting away from the plane, and this is away from the plane, and by same angle. And if you consider these two oxygen atoms, they are in plane. Now if I rotate the molecule on this axis, this hydrogen H1, it takes this H2 position, and H2 it comes to this H1 position, and the orientation, it changes to this orientation. Of course, even O1 and O2, they change their position. So therefore definitely C2-1 operation has been performed on this molecule to give the molecule in its equivalent orientation itself, and definitely C2 axis, it is possible for this molecule. And if we carefully inspect the molecule, nothing else will be possible. We don't have plane of symmetry. So if there was plane of symmetry, then if on this oxygen atom towards the observer, if hydrogen is present, on this atom also towards the observer, there should be hydrogen, but that is not there. So carefully, if we inspect the molecule, we cannot find any other symmetry operations possible. So therefore now this will go to C2 point group, and only operations possible are identity and one C2 operation. Okay, we'll see that now everywhere here. After the example, in the next slide, I'll be giving a three-dimensional view of three-dimensional animation of the molecule. We'll see that now. This is the molecule hydrogen peroxide, and this is called as open book conformer of hydrogen peroxide. See, because so if you imagine this to be on the edge of a book, these two oxygen atoms. So the book it opens in this way, say in V, in this particular way. So now this hydrogen atom, it can be viewed on one side, and the other one, it will be on other side. So therefore this is called as open book conformer of hydrogen peroxide. See, look at this molecule. You cannot have any planes. You cannot imagine a plane here, because this side you will not be having any atom to get reflected on this atom. Similarly, same thing for this. So on this molecule, no other symmetry operations will be possible except C2. So where the C2 axis is, see, C2 axis you can see here in this case, C2 axis. So now on this C2 axis, the molecule, it can be rotated. So I perform the rotation, which brings back the molecule to identical orientation. Therefore only C2 axis is present in this case, and therefore no other symmetry operations. So this molecule, it will go to the point group C2. Okay, the next molecule belonging to the same point group Cn itself, it is C3. So now we should be able to guess here. Now C3, it simply refers to order of axis, whatever is present in this case, it is 3. Order of axis, it will be 3. And now if order of axis is 3 symmetry operations should be possible. Let me make this 3. H should have been 3 here, not 2. Fine, right? Okay, now which should be those 3 operations? Of course, one is identity. The other one, it should be on C3 axis, on C3 element. We shall see that in case of this kind of molecules. 2 operations will be possible, C31 and C32. C3, it refers to a axis on which if the molecule is rotated by 120 degree, it leaves the molecule in indistinguishable orientation. But on such axis, 2 operations are possible. We know this part. On a Cn axis, we can have n-1 operations. So therefore C31 and C32, 2 different operations are possible. Of course C33, that will be E itself, that need not be listed separately. And examples for this kind of molecules belonging to C3 point group. So any molecule which, say, if you have 3 phenyl groups attached. Now when we have 3 phenyl groups attached, their orientation, these phenyl group planes, they will not be identical for all these 3. They will be in different planes. Of course we can see that in 3-dimensional animation. But it will be so that the orientation, it will be so that if we rotate the molecule on this axis, so this phenyl group exactly, it takes up the position of next, and this phenyl group, it takes up the position of this, and similarly this takes up the position of this. So therefore a C3 axis, it can be present here, and pyramidal molecules, all pyramidal molecules of this kind, they come to this category itself. So here A, it can be, say, nitrogen, phosphorus, arsenic, antimony, any group 15 element for that matter. So all those, they can have this triphenyl compounds. So all these triphenyl compounds, they belong to this point group C3. So here also same thing, if you carefully inspect the molecule, except this C3 rotation, no other symmetry element will be possible. And therefore, the molecule it goes to the C3 point group. Let's say it's an emission. This is triphenylphosphine. This atom, it is phosphorus atom, and these three are phenyl rings. See, look at the orientation of three phenyl rings. So those orientations, they are definitely different. Now we cannot have any planes in this case. Say if this molecule it was exactly in a plane which is perpendicular to these two, in that case planes could have been imagined, but the orientation of three phenyl groups is so that we cannot have any planes in this case. What is possible in this case? It's only C3 rotation. So to see that C3 rotation, I keep the molecule in this view. Now the C3 axis, it passes through this. So let's say that C3 axis first. C3 axis, this is the C3 axis. On this C3 axis, the molecule, if it is rotated by 120 degree, okay, it is taking anti-clockwise rotation, right? But the important thing is that it should be rotated by 120 degree. That should leave the molecule in identical orientation. So that's happening here. So therefore, this molecule, it has C3 axis and nothing else. Carefully, we should convince ourselves that no other symmetry operations are possible in this case. So if only C3 is possible along with identity, then the molecule definitely it should go to C3 point group. So this molecule, it is C3 point group. The next molecule, in fact here it is next type of point group that I am considering under MHS will be CNV. So here in this name itself we can understand things. So C, if n is written, it simply means that axis is present. Along with that V, it indicates that along with axis even we have vertical planes. So in any molecule, if we find an axis of rotation, we have axis. Along with that, if we have vertical planes, then the molecule, it will be said to be of this point group, CNV point group. And this point group, it will be called as pyramidal point group, right? When we go to some other examples, definitely we understand why this is called as pyramidal point group, right? And order now, here it will be 2n. So if we have CNV point group, in that case, depending on the order, double the number of the value of n, that many operations will be possible on the molecule. Now, okay, which are these operations? Say identity, it's common, everywhere it is there. And if we have a axis of rotation of order n minus 1 rotation should be possible. Along with that, n number of sigma v's will also be possible in this case of in this kind of molecules. N number of sigma v. So hope we know the term sigma v, or you can just have a quick revision at the previous video where sigma v, sigma d, sigma h, all these things have been defined. Probably third video where planes have been explained. So that idea we should have. What is sigma v? That idea we should have. So such vertical planes, n number of vertical planes will be present in case of the CNV point group. Find one very common example. Definitely many molecules, they belong to this point group. It's C2V, right? So C2VH should be is equal to 4. It should be 2n. So if n value is 2, it should be 4. Now, which are those operations? First, identity is possible, and C2, it refers to a C2 axis. Therefore, on C2 axis, C21 operation should be possible, and n number of sigma v's. So n number of sigma v's, to just distinguish those two sigma v's, it can be represented as sigma v dash and sigma v double dash. Okay, example for this: any bent molecule, triatomic bent molecule of this type, it will be the C2V point group itself, right? So to name some, H2O, very popular one, H2S. So just replace oxygen by sulfur in water molecule. SO2, S it will be here, O2 it will be here. Two oxygen atoms, they'll give bent shape to the molecule. Even NO2, all this, they belong to this point group itself. So here what we can see is, this is C2 axis, right? And plane of the molecule, it's a plane of symmetry. So on the plane, or we can cut the molecule in that plane itself to get identical orientation. So that will be one plane, and the other one, so we can just imagine a plane, right? And in that axis itself we will be having our C2 axis. So that one, so that plane, it will be another plane. So therefore now essentially two planes we have, one identity operation and one C2 operation. Therefore this molecule, it goes to C2. Very important point, this to be remembered. So in case of H2O, both the planes what we have, they are vertical planes itself. So there are chances that this plane, this being planar molecule, the plane of molecule, it can be confused to be horizontal plane. But no, according to definition, horizontal plane is a plane which will be perpendicular to principal axis. But this plane, if you consider, so it contains this C2 axis. So therefore, it's not perpendicular to the axis of symmetry. Therefore, this plane, it's not horizontal plane, it will be vertical plane itself. Okay, let's see now water molecule itself I take and let me illustrate why this both the planes in the case they are vertical planes and not one is horizontal. And of course operations possible and C2 axis how it can be demonstrated in H2O. We shall see it in 3D animation. Okay, this is our water molecule. Definitely C2 axis in this case it has been previously demonstrated. So on this axis I can rotate the molecule by 180 degrees to get identical orientation. So this is the C2 axis. Along with this, so it's CNV point group, it's C2V point group, which means that one C2 axis and two vertical planes. Now let's say two vertical planes. This is one vertical plane. The plane of the molecule, that is one vertical plane, right? So that also includes C2 in this. So it's not perpendicular to C2 and therefore it should be considered to be vertical plane itself. One more plane that is possible is this. This is also plane of molecule. So this also is vertical plane itself because this also includes C2 axis in that. So I hope I need not show operations in this case. Operations easily it can be understood. So in total all these required symmetry elements and symmetry operations are possible so that this molecule, water molecule, it should go to the point group C2V. The next molecule, it's of the same point group, CNV itself, it is C3V. So if it is C3V, simply it means that the axis in this case what we have is of order 3. And number of operations possible or order of point group, it should be 6. For 3, it's 2n, so therefore it should be 6. So which are those operations? First, identity is present, it will be there. And if it is C3 axis, on C3 axis 2 operations will be possible, C31 and C32, and n number of sigma v's. So therefore 3 sigma v, sigma v dash, sigma v double dash, sigma v triple dash, 3 sigma v's will be present. And if we have axis along with that vertical planes, it will be point group CNV. So the point group of such molecule with C3 axis and 3 vertical planes should be C3V. Best example, it's ammonia molecule. So these all are classic examples that I am taking. So what I am intending is once I complete the survey of molecules with one or survey of all point groups with 1 or 2 examples. So later I would like to take random molecules and randomly some molecules and I'll just illustrate you how a point group can be identified when you do not know the point group of a given molecule. So there I'm intending to take some different examples from coordination compounds and all. So here for survey I'm considering the classical examples itself. So for C3V the classical example is ammonia. This is C3 axis, probably this has been demonstrated in previous videos. This is C3 axis, and now planes, where we have the planes. So this each NH bond, if we consider, that will be plane. So that will be so that in 3D animation we can clearly see that this will be so that. So this plane, it passes between these two hydrogen atoms, nitrogen atom and hydrogen atom. So it bisects this nitrogen and hydrogen, and after performing the operation, reflection can be taken in a plane which passes here, and this H2 and H3 it can be taken if the plane is along this H1. So therefore that is a vertical plane because it takes C3 axis into it, and now 3 such vertical planes are possible, and the molecule it will be with 3 vertical planes and a C3 axis. That's how it will be C3V point group. Let's see that in animation. This is ammonia molecule in its 3D form. So now, as I have mentioned in 2D diagram, in this case we have C3 axis that can be easily understood. This is the C3 axis. So always when we are identifying point groups, first task that you should do is we should identify the principal axis. So this is principal axis on which the molecule it can be rotated by 120 degrees. Then this atom it comes, this takes this position. Similarly, this goes here. That will be C3 axis. Now, if at all I have to show sigma v's, 3 sigma v's they are possible. So first one, look at this plane. See this plane, it bisects the whole molecule into two parts, and the two parts they are identical. Or if we perform reflection operation on this plane, then this atom it gets reflected here, this gets reflected here, and always it's true that atoms that are present on symmetry axis, they do not change their position. So this is just one such plane, but by the definition C3V means, so it's C3 axis and n number of sigma v's, 3 sigma v should be possible. Other 2 sigma v's, each NH bond axis, it can be considered to be a plane. The third one, it is this. So totally 3 planes are possible and C3 axis. Therefore this molecule ammonia, it should go to the point group C3V. Okay, last example for this CNV category, it is C4V molecule. So H, it should be is equal to 2n, therefore 8 operations in total. There should be a possibility of 8 operations in this case. And now easily we can guess the operations. Identity will be there. And on C4 axis, totally n minus 1 operations. So C41, C42 and C43, 3 operations will be possible. And n number of sigma v's, therefore 4 vertical planes we should have. So consider this molecule BRF5. So this will belong to this C4V point group. Now C4 axis, it has been demonstrated here. So this is pyramid, a square pyramidal molecule, square based pyramid. So it's a square and one atom, it will be above the plane. So now if you consider this BRF bond, BR and F axial, that axis if you consider, that's the C4 axis. On that molecule, on that axis, the molecule, it can be rotated just by 90 degrees to get identical orientation. So by 90 degree rotation, this F, it can come here, similarly this F here and this F here, this F here. So it's a C4 axis. Now on C4 axis, 3 operations are possible, even identity operation is possible. Now let me show you 4 sigma v's. In total 4 sigma v's are possible. To understand that 4 sigma v, let's weave the molecule along this BRF bond. Let's say we are weaving the molecule from this point, so that we are not weaving this F and BR, right? So F and BR, they are present exactly one above the other, and at this point they are present. And now have not mentioned that. Now we shall see planes. See, this is one plane. This is one plane where these 2 F's, they can be exchanged, these 2 F, they can be exchanged. This is one plane. Similarly, the second plane that we have is this plane. Similarly, this is the second plane. These 2 F's and these 2 F's, they exchange, will leave the molecule in identical orientation. And now one more plane is this. So here the plane, it was not passing through any of the fluorine atom. Here this plane and this plane, 2 more planes are there, they pass through fluorine atom. All these, they are vertical planes itself, right? All these are vertical planes itself because all of them, they pass through this principal axis itself. So they cannot be dihedral planes. The other possibility is that they can be dihedral planes, but for dihedral planes there is necessity of C2 axis. Dihedral plane, it should pass in between C2 axis. But now here what we have is just one C4 axis itself. Perpendicular C2s we don't have. Therefore, no question of sigma d arises. So all planes, they are vertical planes itself. So this molecule, it is a C4V molecule. Let's say it in its animation. This is the 3D model of the molecule BRF5. So one thing what we can notice is that all these 4 fluorine atoms, they are not exactly planar. So they are little above towards this axial fluorine atom. That point can be noticed here. So now here, so this is said to be the example for C4V example. So C4 axis must be present. If it is C4V, that should be C4 axis. See, this axis, it should be definitely C4 axis in this case. So now C4 rotations, you can see the molecule, it can be rotated by 90 degree to get identical orientation. So therefore there is a C4 axis. So by definition, C4V molecule, it should have C4 axis and 4 vertical planes. So which are those 4 vertical planes? See, first vertical plane in this case, it is this. This is one vertical plane, and this is one more vertical plane. So this is one more vertical plane, and this is one more vertical plane. But here in this symmetry at Otterbein, what they have listed is that, so they have gone with that rule, the plane which pass through see these two planes which are passing through atoms, they have been considered to be vertical planes, and these two planes which are not passing through atoms, or which are passing through less number of atoms, these are considered to be dihedral planes in this case. But if we stick on to the definition that dihedral plane is that plane which passes in between perpendicular C2 axis, if we stick on to that plane, in that case we can call all these planes to be vertical planes itself. So essentially 4 vertical planes are present, that is the thing. Right. Then next, last category of point group for today, or in this video, what I'm considering is it's CNH. So this point group, it is even called as reflection point group, CNH point group. See here, this N again, it shows that it's axis it will be present, and along with that H here, it shows that it will be sigma H. And one thing should be kept in mind: if sigma H is present, always it will be 1 in number, whereas sigma V and sigma D, they can be in multiple numbers, but sigma H, it will be just 1. So if the molecule, it has rotation and a perpendicular plane, then the molecule, it goes to the CNH. And even in this case, order of order of point group, it will be 2n. So just double the number of order of the principal axis, that many operations will be possible. Okay, which are those operations? So E is there everywhere, and if I say it's n, rotation axis is present, n minus 1 rotation should be possible, and the next one, it should be sigma H, right? Along with this, even though it's not indicated, when we have a n proper axis and along with that a plane which is perpendicular to that, when these two are simultaneously present, product of these two operations, that's rotation operation followed by its reflection in perpendicular plane, that readily implies that in case of these molecules, improper axis must come. Though it is not indicated here, it's automatically shown that when we have proper axis and corresponding horizontal plane, it definitely, it will be by definition, will be perpendicular to this axis of rotation. So when these two things are there, it is implied that improper axis will be present. So then the other operations, they are possible on whatever number of operations they are possible on Sn. So this can be generalized, so it's a bit difficult. So therefore just I have written that operations whatever are possible on Sn axis. So all those operations, they will be possible in this case. Okay, first let me consider the point group C2H. So C2H means we have a axis of twofold. Consider this molecule. This is trans 1,2-difluoroethene. Trans 1,2-difluoroethene. So now in this case, see this axis. So axis, it has been shown like this, which means that this axis, see, it is from this point, it is coming towards the observer and it is moving away from the observer. That is the axis, right? Or in other words, what I should say is it's perpendicular to this plane, that axis. On that axis, if we rotate the molecule, this fluorine, it comes here, this hydrogen, it goes here. So therefore it's C2 axis. Then it has even a plane, and the plane is this plane itself. This being planar molecule, the plane of molecule itself will be taken as sigma H. This is sigma H because, as I mentioned earlier, axis, it's definitely perpendicular to this plane. So by definition, plane which is perpendicular to the rotation axis, that will be taken as sigma H. So therefore this is sigma H. So along with this, even S2 operation, it will be possible in this case, right? So S2, it refers to C2. Along with that, even sigma H, it is performed. So that is also symmetry operation for this, right? And one more point, maybe later in some other stages I'll mathematically prove this. So this S2 operation, or one operation which is possible on this S2 axis, that will be also identical to I inversion center. See, that can be easily seen here. If that inversion center, it exists here, so this fluorine, it moves in opposite direction and that takes this position. Similarly, this hydrogen, it goes here, and this, if it goes in opposite direction, these two carbon atoms, they also change their position. So therefore even I exists, but I, it need not be said separately. So we can even find that as S2 itself. So if S2 is present, it's understood that this I So therefore usually this I it will be indicated, not S2. But now systematically when we are listing the operations, it's better to first call it as Sn, and when Sn it becomes S2 axis, automatically it indicates that it is I. So this is the point group C2H, and we shall see now all these symmetry elements and symmetry operations in animation. Okay, this is the 3D model of trans 1,2-difluoroethene. So trans, both the fluorine atoms, they are diagonally opposite. Now in this case C2 axis is present, and C2 axis, see this is the plane of the molecule. So this plane, if it is assumed to be plane of the molecule, the C2 axis, so it is this which is perpendicular to the plane. So therefore this is C2 axis, and the plane of the molecule, it can be considered to be horizontal plane for this molecule. So now C2 operation is possible. On this axis the molecule, it can be rotated by 180 degrees to get identical orientation. So that's C2 axis. Then along with that, to CNH point group, sigma h should be present. So perpendicular plane should be present. So that perpendicular plane we can easily see here. This is the perpendicular plane. So on this also reflection operation can be performed. So reflection, if we do, we do not see that, because here itself the atoms they change their position. So sigma h is present. Now there is implied S2 axis. So but S2 it will be called as I here. Usually S2 it will be taken as I itself. So where that I is present, I, it can be taken to be a point, green point, whatever you are observing, that is taken to be I, and inversion operation it can be performed. So therefore S2 it is taken as I, and in this case now the essential requirement for CNH, it's a axis followed by perpendicular plane. Those two things we have, and implied presence of other symmetry elements. So this is C2H. Next example, last example for this CNH point group, it is this boric acid. It is in fact C3H molecule. C3H, it refers to a axis with threefold rotation, and the operations it should be 6, because 2n it is 3 into 2 it should be 6. So which are the operations? So on this E is possible, and because it is C3, C31 and C32, on C3 axis 2 operations are possible. Sigma h will be present. So when we have C3 and along with that sigma h will be even we can have S3 axis. So S3 axis and C3 axis, they will be collinear in this case. So on S3 axis, two genuine improper rotations will be possible, which will be S31 and S32. So therefore totally 1, 2, 3, 4, 5, 6 different symmetry operations that are possible on this molecule C3H. So essentially we need not bother about this to identify the point group. We need not bother about this. We should just find proper axis and a perpendicular plane. So if we have these two things, then readily we can say that the molecule it will go to CNH point group. This is implied that when we have proper axis followed by a perpendicular plane, it's understood that readily this improper axis it will also be there. Okay, this is the example, and this is the C3 axis, just like in the case of the previous example. This, if you take it to be plane of the molecule, perpendicular axis, that will be principal axis. So on that axis the molecule it can be rotated, right? So this is planar molecule. That is very important fact, that this oxygen, hydrogen and boron, all those they are in same plane. And this is sigma h, because it's perpendicular to the C3 axis, therefore this is sigma h, that is also present. And C3 and S3 they are collinear. So what we can do is we can rotate the molecule by 120 degree, that gives a C3 operation. Then further followed by even reflection it can be taken, that will also be symmetry operation in this case. So therefore totally 6 symmetry operations are possible, and because it's C3 axis and sigma h, the point group it is C3H. Okay, let's see the animation of this two. This is the boric acid. Again, boric acid, it's planar molecule, you can find that. So all hydrogen atoms, boron atom and all oxygen atoms, they are present on the same plane. Now this is said to be C3H. This is example for C3H point group. So therefore C3 axis must be present, and C3 axis, this is the axis. So on this axis the molecule it can be rotated. Of course it can be clockwise rotation or it can be anti-clockwise rotation, doesn't matter. So usually clockwise rotations can be considered, then we need not go with anti-clockwise rotation. So this is C3 axis. Now along with that, if I say it is C3H, C3 axis, then perpendicular sigma, the requirement is perpendicular sigma, that you can find here. This being planar molecule, that plane itself will serve as sigma h horizontal plane. So now perpendicular plane is present, which is horizontal plane, so therefore this should be C3H. Now implied presence, so this implies the S3 axis. So S3 axis, definitely it's collinear with C3, where S3 was there, C3 was there itself S3 has developed now. So this is S3 axis. So S3, it includes both. So this axis followed by this plane, both are included here. Now if I have to show operation on this, so just we can find its C3 rotation, then followed by sigma h. It takes place, but will not be able to make it out, because just there itself, this part it comes here and this part it goes here. It's difficult to find that, right? And on S3 axis, this you can mathematically work out. Two different operations will be possible. So it will be S31 and S32. So both are possible on this case. So therefore now this molecule, because of presence of horizontal plane plus axis of symmetry, this will be C3H. Okay, now so I'll just briefly outline whatever has been discussed. It's very important in this case, because otherwise it ends up in confusion. So in summary, in my previous video I had taken MLS point groups, molecules with low symmetry. So in this video I have started with MHS, molecules with high symmetry. So in this MHS, totally 7 different operations are possible. 7 different not 7 different operations. What I mean to say is 7 different point groups are possible in this case, MHS case. So out of that, 3 different point groups they have been considered for today in this video. So first one it is CN, then second one it is CNV, and third one it is CNH. Further, see Cn, if a molecule, if it is to be Cn point group, only what you should have is, except identity, everywhere it is understood that identity is present, only rotation should be possible, then the molecule it will go to this point group, and it has been demonstrated with the 2 examples today. For C2 point group H2O2 and for C3 point group PPH3 example has been taken. Then next we had seen CNV point group. So CNV, along with this Cn proper axis, if we have vertical planes, of course if you can identify one vertical plane, it's automatically definitely other vertical planes they follow, but essentially n number of vertical planes should be present. So axis followed by vertical planes, this we should look at. So when we are identifying point group, we should look for these two things: proper axis followed by n number of sigma ways. That takes the molecule to CNV. Of course, it is understood that no other symmetry elements are present, only this should be present. Fine. Therefore, that will go to CNV point group, and examples for C2V water, it was taken as example, C3V ammonia, and C4V BRFY was taken. And the next one, it was CNH. So here, defining symmetry elements of the CNH point group, they are presence of Cn axis followed by sigma, but of course, implied presence always it should be assumed. So these two, they imply the presence of SN2 collinear with the Cn. That will also be there, but essentially if it is principal axis followed by a horizontal plane, that will lead the molecule to CNH point group. And 2 examples we have seen for C2H trans C2H2F2 trans difluoroethene was seen, and for C3H H3BO3 was seen. So you should take different examples and you should convince yourself that definitely only these many operations are possible in this case, and therefore definitely the molecules belong to these groups itself. You need to work hard, you need to imagining the molecules and identifying symmetry operations by imagining the things. That is very important here. This video, it has helped you in understanding few more point groups. If you have liked this video, you can give like, and for new videos, fresh notifications, you can press bell icon for that. If you are not subscribed, first do subscribe to the channel and share this video with your friends. So thank you for watching this video. Thank you again.